Sound, and I do have sound. Welcome to it's Q&A Friday. What a day today has been. This week has been rough. I don't know about you, but welcome. Q&A Friday, and today it's live, and we're going to just take a look at some questions that have come in. Various questions, a lot of different questions. So, but there's two things that primarily I'm probably going to only hit two questions. The first one is I want to do two things. I want to let you know that I'm working on a curriculum around transformers. And because I get a lot of questions on transformers and the one, well, both these, all of these items are going to deal with transformers today. But I want to let you know I'm working on a document on a curriculum and that I will load up on my website, thomasdimitrovich.com, and you guys and gals can pick at it and hopefully get something out of it. But in the process of working on this, I'm trying to look at some of the questions that have come in around transformers and make sure I include that. Now, what I did was I took a 75 kVA transformer, and I have a presentation. I've got a video on that out on my YouTube site, so you can take a look at that. But I'm expanding on that video because, hey, Chinois Solomon, good afternoon. Good afternoon. So I'm expanding on that video, and I'm putting together some of the details. You know, there's some things that we do that we think that we just do, and you don't really think about some of the details associated with what you're doing or the decisions that you're making, but you just know they're right because at some point in your career, hey, Phil, how do you? I'm going to see you in Florida, brother. Some of these things you do that you just think, hey, this is the way I've done it. This is the way I was taught, but you can't remember sort of why. So that's what I am working on, and I'm trying to put all the details around proper, and I'm looking at the low voltage transformer. So to that end, one of the questions that I'm researching right now, and I hit pay dirt. Transformer terminals. Are they 90 degree? 75 to C? Do I have to use a 90 degree insulation? Can I use 75 degree C insulation? If I use the 90 degree insulation, can I use the 90 degree C column in 310? So I have always associated the 75 degree C discussion with overcurrent protective devices. And so now I'm looking at transformers, and I'm like, okay, in my mind, I'm thinking, well, I can put a 90 degree C conductor, use it at 90 degrees C. We always have to worry, hey, Steve, you always have to worry about both sides of the conductor. So in any case, my journey on understanding the temperature limitations or the temperature values to be used for the ampacity calculation for the transformer application, I think I hit pay dirt. So I will show you a document, and this is what there is a document out on the web, and I'm going to let me find the link for it. I'll put this link because I think if you are into transformer best practices, you might find this. I hope I didn't just close it. No, I didn't. I closed a window. I don't know which window it was, but I closed one. All right, so I'm putting a link out there. Power distribution control systems, transformers, installation, operation, and maintenance manual. It's not the one. I think I closed the one I wanted. There's a document called Best Practices. Let me just do a search. There it is. Look at that. I found it. Here's another good one. This is the one I really wanted to put into the chat. All right. Let me just call it up on my LinkedIn because for some reason, when I put stuff over here, it does not show up on my... Found it. Ow, sorry about that. Okay. Comments. I'm going to put this link, Control V. Okay, so in that document that I just put down into this into the chat out there on LinkedIn and then everywhere else, you should have a copy of it. Except for those of you who are viewing on Instagram, I don't know how to put a comment on Instagram. I can't even see my videos when I go live on Instagram. Other people can, but I cannot. So if you scroll down, conductors. Fire protection. You know what? Conductors. Let me look at the other document. Yeah, in the first document, I think is the one that I wanted. Yeah. That first document, the Installation, Operation, and Maintenance Manual. Really good resource for you to help you understand some of the basics. I would say always follow manufacturer's instructions whenever you're installing a transformer. So when I was looking at trying to come up with what are the lugs rated for, are they 90-degree C lugs? Are they 75-degree C lugs? What are they? I learned that I'm looking for the section in here. Where is it? Dadgummit. There's your inrush current. I'm looking conductor size. There we go. Torque. Okay, well, it's not in there. I'm going to have to find the reference. It's in one of those two documents that I just put up. But I'm going to read to you from the standard, from the UL standard for terminations, for field wiring connections. The standard tells us, and this is standard 1561. That's the UL standard for dry type transformers. Now remember, I'm talking dry type. I'm talking your 1575 kVA, 100 kVA, those dry type little gray boxes that you will see in plants and facilities. It says that a transformer has to be provided with pressure terminal connectors or terminal pads to which pressure terminal connectors may be secured, or the connection of supply and load conductors. And they can be factory installed or field installed. And I learned that most of these transformers are shipped from the plant. You're going to be putting the lugs on, not us. They have wire bending screws. They have a copper, brass, or bond stud for securing the field installed pressure connectors, blah, blah, blah. Leads. Now, the transformer lead of parallel leads or and any connection to the field from the transformer to the field. You have to have stranded copper or aluminum wire, and there's a minimum length of 6 inches long. Now, granted, any of these installations are going to exceed 6 inches because you can't get out of the enclosure, okay? But that 6 inches is how it's tested. So you need at least 6 inches of conductor. You don't need to worry about that because you're going to exceed that no matter what. It can be no smaller than a 14 or a number 12, a number 14 or a 12. 14 copper, 12 aluminum. have insulation. Now, this is the one. This is what get. So these next two items, actually, not this one. The insulation has to have the right voltage. So that's a no-brainer. But the insulation with a minimum temperature rating, 90 degrees C. I was like, okay, so I can use a 90 degrees C conductor, but can I use it at 90 degrees C ampacity? And the answer to that is no. It says 90 degrees C, but sized for 75 degrees C ampacity if the transformer is marked for 90 degrees C field wiring. So this is out of the standard. So the manufacturer's instructions, and I was looking for it in our instructions and the Eaton instructions, and I know it's in here because I found it, and that's what led me down the road of, and I'm going to look for it. Here it is. There it is. All right. When in doubt, just search it out. So let's do this. You'll notice that this is out of one of those two documents. This is the installation, operation, and maintenance. Section 7 says any standard cable of the conductor size specified in 310 can be used. And technically, it should say probably that you can be no smaller than a 14 or a 12, right? Recommended external cable should be rated 90 degrees C, that's your insulation, and sized at 75 degrees C ampacity for encapsulated transformers, and sized at 75 degrees C for ventilated. Oh, 75% ampacity, not 75 degrees C. So 90 degrees C and sized at 75% ampacity for encapsulated transformers. What we're dealing with is a dry type ventilated transformer. That's what you're going to see most often. But otherwise, 90 degrees C at 75 degrees C ampacity. So that's the column you're going to use in table 310. 310.16, right? If I think about the 2020 code, so if you're on the 17 code, it was a different number, 310.15 B16, something like that. So what this is telling me is, now, the way the standard says, it says 90 degrees C, but sized 75 degrees if the transformer is marked for 90 degrees C field wiring. Think about that. When you see something marked for 90 degrees C field wiring, what does that tell you right off the bat? As soon as you see 90 degrees C field wiring, in my mind, I'm like, okay, I can use 90 degrees C, and I'm going to use the 90 degrees C column. So if my full load amps was 135 or 140 amps, I would use a number 1 at the 90 degree C column for 145. Now, I know I got to worry about both ends. The other end of the conductors, if it's landing on a circuit breaker, then that whole conductor is limited to 75 degrees C column. But in my mind, I was thinking, well, if I go to a tap box and that tap box is 90 degrees C, and then I go from there with the 70, so I can make my longer run 90 degrees C. I can land on my equipment at 90 degrees C, land on this junction box at 90 degrees C, and then make the short run into the circuit breaker panel board at 75 degrees C. I can save some money on copper. But no, the transformer says when it's marked for 90 degrees C field wiring, you still have to use the 75 degrees C column, which we probably all do anyway. Okay, which it's probably a moot point. Why? Because, like I said, you're coming out of a circuit breaker panel board or a fusible switch, and you're landing on the transformer. But if you tried to get funky, if you tried to save some money, in the conductor size, what happens, I always tell everybody this, the moment you try to start saving money on a project, the moment you say, hey, I think I can do this, and I'm going to do this, well, it's not necessarily to save money, right? But that's when it normally happens. When you start trying to cut corners, you better cross your T's and dot your I's. So the equipment can be marked for 90°C field wiring, but you still have to use it at 75°C. Now, why is that? Why do I have to worry about 75 versus 90? The reason is because the standard tells you that you're going to test with 75°C ampacity. What's that going to do? If, for example, I had that 130, say it was 140 amps, full load amps. I'm just making numbers up to prove a point. So that's the way it happens, right? So let's say I had 140 amps. Hey, happy Friday, Willie. So let's say I had 140 amps full load amps on the primary of a transformer. Even though it says, hey, this is marked for 90°C field wiring. If I put a 90°C conductor in there, I could use a number 1 because at 90°C, it's 145 amps, and that would be adequate for 140 amps of full load amps. But if I have to use the 75°C column, that number 1's only good for 130 amps. I would have to bump it up in size to a 1/0. So what did that do? It increases the size of the copper conductor. Then the insulation's still 90°C, but I've increased the size of the copper conductor to wick heat off of the inside of that enclosure. So what they do, and I'll bet you if I look, and remember this number, so I'm gonna for my transformer, you know what I'm gonna do? I'm gonna put a comment in here. This is, no, that's the website. Okay, so it's section 10.2 of UL Standard 1561. So section 10.2 of UL 1561 tells us that I have to use a 90°C. It's going to be marked for field wiring at 90°C. I have to use 90°C insulation. I have to, because of the temperature that occurs inside of that little big medium-sized gray box. And I have to use the 75°C column. Okay, so and it says when it's marked for 90°C. If it's not marked for 90°C, then it's 75°C across the board. So it's 75. I can still put a 90°C insulation on a lug marked for 75°C and use it at 75°C ampacity. But I could also put on a 75°C insulated conductor. Not sure how many people would do that. Most of the conductors they're all 90°C insulation. But in any case, not all, but you get what I'm saying. You buying what I'm selling here? So let's take a look now. Let's take a look at temperature rise. What they do for testing and why the size of the conductor makes so temperature rise makes it so important are the temperature rise tests. And I'll tell you from what I understand, the temperature rise tests are the most difficult to pass from a product perspective. Circuit breakers, fusible switches, because what you're doing, and it says transformer shall be subjected to a temperature test. The results are acceptable if A, the temperature at any point is not sufficiently high to constitute a risk of fire or damage to any material used in the transformer. It's a big hunk of iron, a lot of copper and aluminum. I don't know how much temperature you'd have to start that stuff on fire. No temperature rise at specific points is greater than that specified in a specific table. So what they do is they tell you where to place the thermocouples inside of a transformer. And they look at the temperature rise. And they have a specified ambient temperature. And they make sure that you don't exceed a specific temperature rise. Now, all right, transformer marked with a K factor. They talk about K factor transformer. So let's go to table 23.1. So I got to search for 23.1. That's the temperature rise table. 23.1. I'm looking for it. Okay, here we go. Field wiring conductor current rating of 100 amps or less, 20 degrees C, temperature rise. Field wiring conductor current rating of greater than 100 amps, 35 degrees C, temperature rise. At any point within a terminal, okay, so D is at any point within a terminal or wiring compartment that a field installed conductor might contact, including such a conductor itself, unless the transformer is marked in accordance with 3812.3. Let's see what that one is, 38.12.3. So, any point on the exterior of the transformer enclosure, except as indicated in 23.2.1, and they tell you the insulation class, 105, 130, 135, the hotspot differential, ambient hotspot differential, and they'll tell you 55 degrees C, 75, etc. So they give you the temperatures on the outside. The polymeric insulation materials, the bolted joints involving aluminum or copper, except where lower limit is specified in D is 65 degrees C. And there's an informational note A to which one is this? Yeah, to both A and B. A says the temperature on a wire terminal or lug is measured at the point most likely to be contacted by the installation of a conductor installed as in actual service. And B is if the rise is 35 degrees C or less and an aluminum bodied connector is used or aluminum wire is intended, the connector shall be marked AL7CU or AL9CU. If the terminal temperature rise exceeds 35 degrees C but does not exceed 50 degrees C, the connector shall be marked AL9CU. And it tells us for additional markings to go look at 38.12.3 and 12.4. 38.12.3. That's a marking requirement. We already talked about that one. So let's go take a look. And it says, it talks about the thermocouples are to comply with the requirements specified in tolerances on initial values of EMF, etc. A minimum of 4 feet of copper wire is used to be attached to field wiring terminals. The size of wire to be used is to be the smallest size, having an ampacity in compliance with 21.4. Table 23.2, we're going to go look at that. 21.4, table 23.2, 23.2. Oh, there is ampacities of insulated conductors of at least 100% of rated current or for the circuit involved. So, and look at this, 75 degrees C. 23.2 is ampacity of insulated conductors. 150 degrees for a 1-aught. 150 degrees for a 1-aught. That, yeah, 75 degrees C. The RC blows Cupcake Island, right out of table 310. So now let's go look at 3812.3. 3812.3. Are you guys having fun? Because I am. I'm learning. I am learning something. 3812.3 says, if during the temperature test, the temperature rise on a field installed lead or on any part within the wiring compartment that the lead might contact if installed in compliance with the marking in 3812.5, we're going to look at that one too, is more than 20 degrees C, the transformer shall be marked at or near the point where field connections shall be made and so located that it will be readily visible during installation. With the following or equivalent, use wire rated for at least degree C and sized on the basis of 75 degrees C ampacity. The temperature value used shall comply with 38.1. So there's markings inside of the transformer that you may or may not see based upon section 38.12.3 and whether or not they had a temperature rise more than 20 degrees C at that lug, at that termination point. So what this is telling me is temperature rise, your conductor, even if you see 90 degrees C, you've got to use the 75 degrees C column always on a transformer, always. Even though there's no circuit breaker in there, it's about the amount of temperature that's in that enclosure and whether or not you're going to exceed that 90 degrees C insulation. So you might need a larger copper conductor to wick that temperature off of the equipment outside or out into the, you're just addressing the temperature buildup inside that transformer. Tell me that is not cool. All right. It's not hot, right? So in any case, that should answer the question of, is it a 90 degree C lug? Is it a 75 degree C lug? Can I use a 90 degree C conductor at 90 degree C? Remember, you always have both sides of the conductor. So even if the transformer was 90 degrees C and you can use it at 90 degrees C, if it's coming out of a panel board with a circuit breaker, it's going to be 75 degrees C because the limitation is on the other side of the conductor. But if you took that transformer from the lugs of the transformer out to a tap box or a junction box that had 90 degrees C terminations in it, and it was a 90 degree C enclosure, you still would have to use it at 75 degrees C because of the restrictions and the limitations of the transformer itself. And there might be other markings inside that transformer or in the instructions, just like these, where it tells you any standard cable is be rated 90 degrees C. So it's telling you you have to use 90 degrees C insulation and at the 75 degrees C ampacity for this transformer, right? So always follow manufacturer's instructions. Always follow manufacturer's instructions, period. I learned something today, and I hope, and we learned it together. Okay, so now the other question that came in, one of my buddies on my YouTube network, my Tubin network, and you can go out to my YouTube site. Please go out to my YouTube site. I'm asking you nicely, get out there to my YouTube site and make sure you subscribe. I look forward to seeing you online there. I've got a lot of materials out there, very similar to this. And go and check out Thomas Dimitrovich. Hey, we got Ireland in the house. Go out there and check out thomasdomitrovich.com. I'm working on a curriculum, and it's going to be out there pretty soon, but you can subscribe out there. And we're working on 70E documents. We're working on National Electrical Code Changes 2023 code cycle, and I'm going to start working on a 70B. We're going into second draft meetings for 70B, so some significant changes coming for maintenance. All right. Another thing you got to think about. All right. So this question, I'm looking for it. Can you please explain why overload protection can be placed anywhere in a circuit, while short circuit protection needs to have an exact location? This gentleman does not. And we're online. Doesn't understand the motor analogy. So what I'm going to do is, and I'm going to try to explain that. I know it can be confusing. So let's just talk about. Let's talk about this. I need to get the right screen. Okay. So, and I'm going to fix this a little bit, make it a little larger. Meanwhile, Tommy's getting larger. Right? I'm going to make this a little bit larger. And actually come all the ways down. Look at that. Okay. First, let's talk about the difference between a short circuit current. Let's talk about what a short circuit current is. Okay. When you think about a short circuit current, short circuits can be higher or lower depending upon where the short circuit occurs in the power distribution system. Right? So, and I'll tell you why that is. I'm going to use my pen. The fault current up here is 31,400 amps. The fault current down here is 5,000 amps. Why? I have impedance in a transformer. I have impedance in that conductor. I have impedance on the secondary conductor. All of that impedance will knock the available fault current down. Now, it is true that for a fault at this point, all of the current will flow from the utility down through that transformer, down through this overcurrent protective device. But let's say that my fault on a circuit, can I do this? I'm going to try to do something here. I thought I could black it out. Nope. Okay, let's say that I'm going to go to another analogy right here. So when I have a circuit, and this is, say it's a single phase, and I have my positive and my neutral coming back, and I have a load going through in that circuit, right? An overload, all of the current stays in the path. So I can guarantee in overload conditions what the current is at this point will equal the current at this point, will equal the current at this point, will equal the current at this point. That current is always going to be the same. Why? Because I have an overload and all of the current is staying in the same circuit. Now, if I have a short circuit, now I had a fault that could take a portion of the circuit out. So if, for example, if my overload protection was right here, I would see my overload. I would see that overload. If my overload protection was right here, I would see that overload. If my overload protection was here, I would see the same overload. I always see the same overload as long as I'm in that branch, right? I can put my overcurrent protection here. I can put my overload protection here. I can put my overload protection there. They all see the same current because they all stay in the same path. But if I elected to put my short circuit protection here, and I had a short at this point in my system, everything downstream is out of the picture. It no longer sees because all of my current is flowing through the short circuit. It's not flowing down here. So now I would not have short circuit protection for that portion of the circuit. That's why it's important. That's why I can locate overload protection in a series circuit. I can put my overload protection like in a motor circuit. That's basically where we were going with this. Was we did a motor circuit analogy, right? So if I was dealing with a motor, hold on. Whoop. I'm hitting the wrong buttons. If I was dealing with a motor, so I gotta close this, discard, and I want to minimize that, and I want to maximize that, and then I got to get to the right spot. Here we go. So if I was if I'm looking at this motor circuit, whether, let me just get it all on the screen. All right, so if I was looking at this circuit, my overload protection, is here. If my overload protection was up here, it would see the same current. If my overload protection was down here, it would see the same current. But my short circuit protection has to be up at the head of the circuit. And I use that same analogy with regard to protecting a transformer. And the reason I do that, discard. The reason I do that is because if you think about a transformer, and let's go up. If I think about a transformer, draw. I've got a transformer. I've got a breaker on the secondary, and I don't know, I'll put a fuse on the primary just because I screwed that up. That's a fuse. And I have a secondary breaker. So if I put a big load on this transformer, all of the current is going to stay in the path. The current will flow through the transformer. They'll have two different values. The primary will be different because transformer does its job in transposing current. But I can't overload this transformer because that breaker will stop the overload. And remember, when I'm plotting my curves, I'll plot my transformer damage curves up here. I might have the primary fuse protecting something like that, and my downstream breaker might look something like this. So that is that circuit breaker. So this circuit breaker is to the left of the transformer damage curve, and because all of that current is going to stay in the path because it's an overload, then I will provide protection for that transformer. If I have a fault inside this transformer, then that's when the fuse provides the short circuit protection, and it is upstream because I can't put it downstream, because if I had a fault in that transformer, all the current goes outside of the path. Everything down here doesn't see it. I get a collapsed voltage, and my secondary breaker, even if it opens, it's not going to open because the fault is upstream of it. The party's going on behind it, not in front of it. So that's why when I talk about transformer protection, when I talk about that transformer damage curve, I say, look, you don't have to worry about the transformer damage curve on that very tall piece because the secondary breaker provides the overload protection. The primary overcurrent device, whether it be a circuit breaker or a fuse, will provide the short circuit protection for the transformer. So hopefully that helps you understand that. And you get it now. Excellent. 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 Well, I'm glad you got that one. And I'll tell you what, I just learned something else about transformer lug terminations and their temperature ratings. Hopefully you guys got and gals got something out of that as well. So thank you for that. And thanks for that question. All right. So those were my 2 items today. That's all I was going to talk about. That's all I have time for. And it's 12:39. I was going to try to go until 12:30. I've got a 1 o'clock call that I got to prep for. And I got to make another phone call to call Mr. Finnan back. I missed his call. I called him and said, hey, can you call me? But that's okay. I'll call him back. All right. That's my Q&A Friday. We're keeping it shorter today. Hopefully that's a good thing. I don't know. You might say you like the 1-hour sessions, but that's all I have to say about that. So what I will ask again, please don't forget. Don't forget to do what? Subscribe. Subscribe to my YouTube channel. Go check out thomasdimitrovich.com. I'm going to be expanding my transformer information on my website. And we're going to put up a little course up there and see how you guys and gals do. And I'm going to put quizzes in there as well. And there will be information just like what we talked about today with regard to that 90 degrees C versus 75 degrees C discussion. And a lot of other little tidbits of information that I'm learning about proper application of a transformer, the installation of a transformer. And I'm focusing on a dry type transformer. That's the one so power systems design on Tech Thursday. You know what? I am, I'll tell you what. I sort of got off of, just because of everything else that's happened. I think it was since 70B is creeping back up again. So on the power systems design, I've got to think about, I'm trying to lay out the outline for that, to be honest with you. And I have been working on, maybe I focus it on a commercial building. And then you've got to think about, how do I put together the one-line diagram? How do I do my load? It really starts at the load calculations. And I don't have much on load. I have a course on residential load calculations. I don't have one on commercial building load calculations. And the first thing I've got to put in there is talk about, how do I estimate, right? Because I haven't broke ground yet. I've got to quote a job. I need to put together the specification. What size service do I need? I've got to estimate based upon minimal information. So I'm working on that right now and trying to put that together, and I will do something. I just have to get my butt back in gear on that one. So yes, I will be putting that stuff together, and this transformer one will be a part of that as well. So anyway, I just got to figure out a way to skin that cat. All right. Thanks, everybody. Dan, thanks for joining, and appreciate you dialing in. And Philip, yeah, commercial Phil. That's I think. I know. I think so. I'm multitasking, and Phil. I think a commercial power. Well, my goal is to get a sample building put together. So, and I want to say, look, this is my vision. I want to say, you were just approached with, here's what you would get from an architect. How do you put together an electrical safety workshop coming soon in Jacksonville? See you there. So my goal is to say, how do you put together the project? How do you go out for bid? You haven't even broken ground, figuring out the size, the distribution, how many panel boards you're going to need, all that good stuff. Go through that process. Then, and I want to use an actual project, right? So I want to say, here was the bid package. Here's how we put the prop. This is what we ordered for the job, and then and then follow it through the design process, like transformers. And what I'm talking about right now, sizing the transformer for the right size, figuring out the conductors, the pipe, all that good stuff. So I'm working on all of that. I just got to figure out how to put that in order. And don't forget, like Phil says, the Electrical Safety Workshop, Jacksonville, Florida. Phil's going to be there. I'm going to be there. And we are going to have a blast learning electrical safety. And remember, there's hospitality rooms in the evening. There are meet and greet opportunities. It is just an opportunity to network and learn. So I will look forward to seeing, Phil and I will both look forward to seeing each of you down in Jacksonville, Florida. You can still sign up. You can still register. There is a trade show associated with it as well. And I am going to live stream from the trade show. So I'm going to be, we're going to have in our booth, we're hopefully going to talk to people in person in our booth. And Phil, if you're going to be there, I'd love to get you on tape as well to talk about electrical safety and the fact that this would be your first electrical safety workshop. I got to find out boy, you got me charged now. Electrical safety workshop. When is let's take a look at the program schedule. Excellent, Lewis. Excellent. Don't go out there and check it out. I believe when is the general session? I think is it Thursday? Hospitality, maybe it's Tuesday. General session, opening reception, tutorials, ESW lunch, general session, product and services exhibition, 3 to 6 on Wednesday. So if you're coming in on Wednesday, Phil, we're going to get you on. Well, you and I are going to sit in the Eaton booth, and we're going to talk about electrical safety, electrical safe work practices. What you're, as a first-time attendee to the electrical safety workshop, I'd love to hear what you have to say about it. And I know you're not shy, so you're going to be there. Awesome. Excellent, Phil. Excellent. So 3 to 6 p.m. Eaton booth. See you there. And for anybody who can't make it to the electrical safety workshop, I got all the equipment down here. I've tested it. I just got my little mobile internet, and I was able to live stream from this A10 Mini Pro. I've got an Ada camera. I've got my Rode microphone, and we are going to be live from the Eaton booth at the electrical safety workshop talking about whatever. It's going to be safety related. So I am looking forward to that. And Phil's going to be can't get there till Thursday. Phil, oh my gosh, I was counting on you, brother. I thought you were coming in on Wednesday. All right. Well, you missed the opportunity. You know what? I might be able to set it up because it's all my equipment. We might be able to set up somewhere else in that. We might be able to set up somewhere else inside of the hotel. We're going to figure this one out because Phil, you and I got to go live. We got to go live. We got to sit down together and talk about stuff from the electrical safety workshop somewhere, and it's all mobile. So and I fit it all in my backpack. It's awesome. You're going to your jaw's going to hit the ground when you see this setup. Jervin Tegpuno, for a client with a 440 volt 3-phase and 230 volt single-phase load requirements, what is your idea for its power system? Well, I'm thinking to have 13 8 kV to 440 bank, then have a separate 440 to 230. Love to hear my ideas. You know what? I am going to write that down because we're going to be jumping off here. Dan Bumbernick, yes. San Antonio, we work together in different projects. Absolutely. Dan's a great guy. Great guy. Wednesday night, 7 to 8. Phil, we're going to have to do something there. All right. Okay. And Jervin, I'll take a look at your comment and I'll see if I can't answer it. I'll take a look and have a suggestion for you. All right. All right. Thanks, everybody. Remember to have a great weekend. Stay safe and please stay healthy. And I really appreciate everything that each of you does for electrical safety and the electrical industry. Thanks for tuning in. Don't forget to subscribe, hit the bell. Also, go check my thomasdimitrovich.com. And if you go to thomasdimitrovich.com/resources, and log in there. If you go to thomasdimitrovich.com and resources and sign up for the members only registration, you will have the ability to do a lot more great things and get involved with some other things that I've got going on as well. So please check that out. And I look forward to seeing you online. All right, everybody, got to drop off. Take care, stay safe, and please stay healthy. Till next time. Have a great weekend.